Thanks, John. Here they are, 1/6 scale drop model. On the Bendix model, they later on we decided we'd like to see what it's going to do on soil surface, so we added sand and stuff. And it turns out that the lunar surface is about like beach sand as far as the compressibility of it. So we experimented around, and there was a lot of experts here what the lunar soil water. It's absolutely amazing when you don't have any data how everybody can be an expert. And I love to understand all of it. And of course, growing in the full scale Langley, 6 scale JSC next. Grumman, I think, was ahead of the game on being able to develop the simulation time domain solution of the lunar module landing. And they essentially had a time domain solution for aircraft landings. And they just modified their aircraft lander to the lunar module, and it had 6 degrees of freedom, rigid body degrees of freedom. It's CG, 3 translation, 3 rotation. Then later on, here at JSC and at Langley, we developed our own 6 degree of freedom simulation. This was the early work. This was before Grumman, or it might have been in parallel. That Langley, if you think of a 4-legged lander hitting, you think the minimum stability is going to be across the foot paths with the lowest overturning radius. So in that period of time, we called it a 2-2 landing, 2 trailing gears, 2 forward gears, going downhill, and that would produce the most be the most unstable configuration. Whereas a 1-2-1 trailing gear, 2 side gears, and then the forward would produce pretty stable because the overturning radius is high. But Langley, in their early works, identified that that's not the case. They were finding their instability is about 22.5 degrees. If I say I got a 1-2-1, and that's 0 attitude orientation, and I rotate it 45 degrees, I get 2-2 landing. Well, they were saying the minimum stability is occurring around 22 to 25 degrees. And they had test data to prove it. So, and one of the big deals, I was just getting started back in this particular period, and I remember talking, give me the next chart. Well, I remember talking to this guy named Bill Walton. He was at Langley. He was the one that did all of the theoretical aspects of this and correlating with the stability. And I did develop this program similar to what he had. And I remember calling him up one day, and I said, and all he was using for the model on the ground reaction was just CX dot. He just takes the velocity of the foot pad, multiply it by some constant, and he was getting excellent correlation with it all. And I said, well, what did you use for C? He says 50. And I put 50 in my program, and I got identical results. And I'll tell you, if you got a 6 degree of freedom program and you don't have a good closed form solution to check it with, it's tough trying to figure out whether or not that stuff's telling you the truth. But once he started that, it gave me a lot of confidence that just all this stuff does hang together. We started out with 3, 4, and 5 legs design, and we started out with an inverted tripod, and then you got to what they got right now, the cantilever case, which is the 2 secondary struts attached to the primary strut. After iterations on that, we considered the 3 legs to be the lightest but most unstable, and the 5 legs to be the heaviest but more stable. So as you can tell, what's left over? We went to the 4-legged. And again, there was 2 basic designs, and we ended up the inverted tripod design attached all of the struts at the foot pad, whereas the cantilever case, the 2 struts were attached to the primary strut. And that gives you a little bit more room in case you hit a boulder or something, you wouldn't be poking a hole or breaking one of the struts if they were up higher off the ground. And you can see in the configuration later on. Next chart. Again, we use collapsing honeycomb, aluminum struts with the honeycomb cartridges. And at the first level on the primary strut, I think started to crush at around 5,000 pounds. And I think the second level was around 9,500 pounds. And in the secondary struts, they could stroke in both tension and compression. They had tension. If it was being extended, we had about a 500 pound for about 4 inches of the honeycomb would collapse at 500 pounds, and then it would go on up to something like 3,000, 4,000 pounds. And by the way, in our testing, we couldn't get them to give us precision honeycomb like they're going to put in the real limb. We just had to get take what we got, and they would do some cut rush test on it, and it varied 10% between one batch to another. So you might have 500 pounds on one strut and 550 pounds on the second, on another strut.
Excuse me.
But they had enough control.
Did they just not have enough of the material to test with, or was there some?
No, I think they just they kind of thought the test program for these little models was kind of not too important, and so they just give us what would come out of the machine.
Okay.
That's all. I just thought that was just some manufacturing tolerances. Some of it might be minimum gauge, some of it might be maximum gauge, things like that.
Huh.
I don't know. Your next shot. Okay, here's the basic dimensions of this, the lunar module. Here was that probe I was telling you about. It's basically about 31 foot from 1 foot pad to the next. And I think the CG, I don't have the CG height here, but the Apollo 11 limb, we computed its weight, or computed its mass to be about 480 slugs, so multiply that times 6, and what is that, 1,800 pounds on the surface. That's short. Now here's what here's our velocity envelope. The vertical line is sink speed, and the horizontal line is horizontal velocity. And we did all our Monte Carlo stuff, and we said, okay, you had 9974, you're going to land in this envelope, in this spot right here. Well, where he landed was right there. And we're going to talk about that some more too. But coming up with this, we started out with 10 feet per second here, and went over to 5. And you can see, well, we are not doing too good because we were violating that envelope. And so then we cut it down to what we call the doghouse, where it's plus or minus 4 feet per second, 10 feet per sink speed. And that point right there is the highest kinetic energy point. We decided that we'd use a 6-degree slope, maximum 6-degree slope, with a maximum depression of 24 inches. Well, that turns out, for this particular geometry, to be about 12-degree effective slope. So we were good anywhere in this doghouse. Next chart. In our design condition, again, we constrain the foot pads. Anytime you unconstrain the foot pads, let it slide, you're increasing stability and you're relieving energy absorption from the landing gear. And so here was kind of our 4 design cases. We're looking for a secondary strut. Was going to pick an orientation that really taxes the stroking of secondary struts, and it would have been landing up into the hill in that particular direction. Then we got a downhill landing, and And we got our one taxes the primary strut stroke to maximize it calculating, which is 1-2-1 downhill. Next chart.
Question? Okay, I guess maybe I'll ask after you finish the next slide.
Back up one. That one?
No, I said I'll wait until, I just saw
Oh,
you
okay.
move to the next slide after this.
Okay, well, right before, and I remember doing this work, we did 1,200 Monte Carlo runs, where we would take the lunar orbit photographs on the top, the typographical features of the lunar surface, and randomly come up with a slope. We just pick a spot, say that's where we're going to land. What's the slope at that point? And we generated, and we did the Monte Carlo on velocity vector, and we ran the 1,200, and our criterion on slope, if it turned out to be greater than 12 degrees, is that we can discriminate against that and throw it out. We won't land on it. And the procedure was, I mentioned that little probe. You come down to the point that probe makes contact with the lunar surface, light comes on in the cockpit, pilot's supposed to hit the button, kill the engine, and sinks right in. And so we did, that was our procedure. And he had a little Monte Carlo on the time delay. Some pilots were quick and some were slow and so forth. And the thing would be is, the closer you get to the lunar surface with the engine thrusting, reduces your stability quite a bit, because it acts, if you snag a gear, the thrust kind of acts to turn you over. And so we went through all of that, and I gave a briefing, because there were some astronauts and the management, and I remember Neil Armstrong was in the crowd, and he said, well, I don't know whether to say George or Zupp. He said, well, that's a good piece of engineering, but I'm not going to land it that way. Next chart. He says, I'm not going to land it till I'm convinced the footpad is firmly on the surface of the moon, which means he's going to be thrusting all the way down to that point. And boy, it just, well, now we're over-designed from energy absorption, because he's not going to crash it in, and his landing envelope is quite a bit shrunk, because now he has a tendency to turn it over. But he's landing so low, so slow, that everything turned out all right. The other concern was, in this case right here, this is Apollo 11. Here's the probe. He's coming in, and here's, looking forward is that direction, and it comes out and climbs down this ladder. And gets off and does what he's supposed to do. But you can tell we got plenty of clearance right here on the engine bell. Some of our cases, we're actually having the bell dig a hole underneath with the plume of the engine. Again, you can see these gold wrapping here, and that was done, I think, primarily for thermal consideration.
That's gold wrapping?
It's gold wrapping, yeah. A gold colored, I don't know if it's, I'm sure it's not gold. Well, he was basically coming this way, out of the, translating up the hill, and here, give me this. I don't know, yeah. Oh, this is kind of close up of that probe, and you can see he hit and just kind of rolled it over. And there's the foot pad, and I was hoping to see it. This one right here, I don't think you can get that, but you can see this dirt, this lunar surface piled up in front of it. And that was about the way the artist's conception had it in '67. So some people have got it, some don't. Next chart.
Does this switch between each?
Oh, here it is, yeah. Yeah. There's a lunar surface kind of piled up. Now he's translating sideways. He's looking this way, but he's going this way into the hill. Next chart. One of my objectives here was to identify what kind of bearing strength the lunar surface has, what kind of friction coefficient, so forth. So So I just said, well, I will go in and just say, okay, the vertical force acting on the pad is some constant I want to identify times the foot pad penetration. And I would jockey this around until I thought it was producing about the right result. And I said the horizontal drag force was going to be a friction coefficient times the vertical force. And I wanted to put some kind of plowing coefficient in here. And it would be some constant times the skid distance. And of course, this model right here, you got to be careful because if you're backing out, this goes to 0. Next chart. Apollo 11, here's what the touchdown rate. This is pitch, roll, yaw, which you can tell is very small. And here's the velocities. This is its sink speed, and this is its forward velocity down the y-axis, and this is the z-axis. So what I did, I programmed these soil equations into our computer simulation, and I took the pitch, roll, and yaw rates and see how best I could correlate those two. Next chart. Now here's, to me, this is, you can claim the bragging rights on this one. Here was our predicted versus measured. I thought that was a pretty good fit. And that gets, it doesn't kind of degenerates. That's on pitch rate. Next one. This is yaw rate, and we didn't do quite as good there, but we did have it on the same side of the curve. Next one. This is roll rate. Roll rate is not quite as good, but we did okay. Next chart. Here was a measured strut stroke. All the stroking occurred in the secondary strut and the tension side. And you can see no data available here. And 3, 2.5, something like that. And let's see. Okay, next chart. Here's our predicted values. There you go. Yeah, these are predicted. So we're in about the same ballpark. The other thing that was kind of difficult to put a handle on was when he was landing him, we had the data on the descent engine, you know, when he shut the engine off, so forth. And so I had that profile programmed into our landing simulation. And I did model probe, the contact probe forces, but buckling that. Next chart. And if you do all of that good stuff, here's the range of parameters that you have. 0.3 for the friction coefficient. Our range varied from 1/4 to about 0.4. That we could, and it just, my judgment, I said, okay, I think 0.3 gives the best correlation. And then I said, what's the bearing capacity? Turns out it's about 5.3 psi per inch. And again, that range was like 4.6, 5.9. And the plowing coefficient, this is just artificial, but I just use 100 pounds per foot. And the measured slope, I mean, the slope is somewhere in that range right there. But you can still get results. The point is, you're just talking about tenths of degrees. So. Next chart. And just summarizing what we found, that's a typo right there. It should be 0.3. Conclusion was, it's more than adequate to support the limb weight, and if it's more than adequate to support the limb weight, it was not going to be a threat to astronauts walking around on its surface. Dust generated by the limb descent engine, it was there, but it wasn't detrimental to the, point where it was, putting the landing in jeopardy. And one of the things I might point out is an observation on my part, it was a bunch of people's part, but, one of the reasons we had success was we had decision-making down at the engineering level. Like if you were a subsystem manager or something, you can get an audience with the program manager within a day, sometimes that day. And it's always a good idea or a good thing to do to make sure you knew what you were going to do to get out of this mess we're in. And don't rely on going to the program manager and him telling you what to do to get out of the mess. Because sometimes the mess can get bigger. Next chart. I think that's about it. That's all I have. I was gonna, you know, I always want to do a little bit more than I've done, but I've got photographs of the other Apollo landing sites, and what I was trying to do is to infer, based on Apollo 11 data, that these other landing sites are equivalent.